thing is true is that energy before equals energy after. This leads to some very interesting things. Let's say I have a ball A moving at velocity A, ball B moving, and then afterwards they would be going different velocities, right? If it's elastic, the way I write my collision, my momentum is still the same. MA VA plus MB VB is equal to, I'm going to call it MA VA prime, prime meaning afterwards in this case, plus MB VB prime. Momentum's conserved. Well, we just did a whole bunch of those. That's boring. But at the same time, kinetic energy is conserved, right? We're talking about kinetic energy, so this would also be true. Well, it's kinetic energy plus kinetic energy equals kinetic energy plus kinetic energy, right? That's what would happen, right? We're not making up a new formula. You knew this from last chapter. The difference is that now we're talking about doing both at the same time. And because of that, we have two equations, he says with a smile. Before I move on, though, it says, well, it would be completely elastic. The phrase completely elastic on your AP test is going to refer to when two objects stick together. That's what it means. That is the maximum way to lose energy is to stick together. That's called completely inelastic. That's about all we're going to talk about it, except that when you see the word completely inelastic, you're supposed to think, oh, they stuck together.
Wait, well, what if they keep moving together?
They will.
Okay.
But it's the maximum amount of energy you can lose in a collision is when the two objects stick together. Okay, so we call that completely inelastic. Feels like completely inelastic should mean all the energy's gone, right? That's not that's not the phrasing they use. Okay? Completely inelastic means they lost the maximum they could possibly lose, which is the two objects are still stuck together after the collision. Which is why things like car accidents, when they usually do stick together, there's a lot of heat and sound going to be associated with that particular incident. Whereas when two beach balls run into each other, even big beach balls run into each other, there's a cord. That's it. Okay. If you want to know the difference, let me do this for you. I have here something that I usually mess with kids with, but I'm not going to mess with you as much on. I have two balls here. These were made. They're the exact same plastic. One was made in a process by which air was allowed to form in bubbles inside. Okay. So that's your standard Super Ball. Doesn't give you everything back, but it gives you a lot of it back, right? You can hear the noise, right? Whoops, I have two. Hold on. That wasn't a great demo. Mr. Resney, you can do better than that. That's it. Okay, ready? Take two balls, right? Whoop. Which one made more noise? That one. Okay? Even more so. Right? See how high this bounces now? Now this is lower than this one. Ready? Same ball. Does it bounce as high? It made more noise as it bounces high. Completely inelastic. Okay? Stuck together. All right? What?
So, for trampolines.
For trampolines?
Yeah, if the surface was, I don't know, quieter, you'd jump higher? Maybe.
Yes, you bounce higher if it's quieter. You can make the trampoline a quieter device. Also, by the way, as a safety feature, a lot of trampolines are designed with metal springs that aren't quite really well put together. And the idea is potentially to take some velocity off of the poor child bouncing up and down, because they don't want you to kill yourself bouncing off the trampoline. Question over there? No. Then let's do the first one, because this is great. We're going to use every Emily. We're going to use every Algebra 1 skill you learned. Every last one of them. If you didn't use them all, you didn't do this problem correctly. Here we go. Number 3. A ball of mass 4 kilograms is moving with a speed of 5 meters per second when it collides elastically head-on with a 2 kilogram ball moving at 2 meters per second. What is the speed and direction of the two balls after the collision? So I've got ball 1, which is 4 kilograms, which I'm going to draw as going this way, although it might not be. I'm going to call that B. What do you want to call that? Velocity of the big ball?
BB. BB.
BB. Velocity of the big ball. And then I got 2 kilograms. The 2 kilogram, what's its velocity?
LB.
Little ball. Okay, why don't I just
Wait, are
use
they
L
in
and
the
B?
same direction?
Well, not necessarily.
Wait, I don't get how this is any different than like. the-
It's not any different, except it is. Here we go. All right, so what speed and direction of the two balls play? So I'm going to use momentum before momentum after, because as Emily just put it, isn't this the same? I've done this before, right? So I've got 4 times 5 equals, sorry, that's wrong, plus 2 times negative 2, be careful with that, is equal to 4 times the velocity of the big ball afterwards, plus 2 times the velocity of the little ball. I've repeated it several times before. Can I solve this?
No.
No. When I can't solve something because it has too many variables, what must I do?
Find another example.
I need another equation. You may suggest an equation that might involve elastic collisions.
Energy.
Energy before equals energy after.
Oh,
No.
Energy before is going to be kinetic energy of the first ball, which should be 1/2 4 5 squared 1/2 mv squared
Plus 1/2.
plus 1/2 mv squared equals 1/2 4 vv squared plus 1/2 2 vl squared. Little ball and big ball.
This is a lot of.
All right,
This is terrible.
Yeah, what the heck?
we're done, right? We had 2 grades, 2 and notes. The rest is just algebra. How hard can it be? All right, let's do it.
It's funny.
Isolate variable. Let's see here. Nix is going to tell us which one to isolate. Which one to isolate, Mr. Nix?
the little one.
The little one. Good call, sort of. Here we go.
Okay.
So I move this to the other side. I go 16 minus 4VB equals 2VL, right? Divide by 2, I get 8 minus 2VB equals VL, which makes it a very logical choice because it gives you nice big numbers. Rather than the other choice, which gives us fractions, and we hate fractions because they scare us. Like we're little children, we're scared of it.
I think the opposite of this
Wait,
well.
what?
So what? Anyway, don't worry about it. We isolate variable. We're good. Move on. I got 1/2, so I'm going to do the work here. I got 50 plus 4, since it's 54, equals 2 VB squared plus parentheses 8 minus 2 VB squared, right? Because 1/2 times 2 goes away. I'm going to pause there because the math is icky.
Wait, what?
Ah,
This is a bad day for all of us. Teacher.
Okay? Where does the 8 come from? It was this part of this thing, right? So I'm taking my VL and I'm plugging it in with a square on it.
So is this a quadratic?
So I'm going to have to FOIL this, aren't I? Don't you have to FOIL this? Because they have a minus and a square on it. I have to FOIL that. In addition to that, if there's a number out front, I'd have to distribute it. Now, fortunately for this one, we did 2 and 1/2. So therefore, I'm not going to distribute. So you might get off not having to distribute on this problem. But that's the good news. So now move forward, 54 equals 2 VB squared plus, oh yeah, 64 firsts, outers, 16 VB, inners, 16 VB, lasts, 4 VB squareds.
is that all square or just
It's the B little subscripts B, right? That's we're just saying which kind of B we have.
Quadratic equation.
Oh yes, we're gonna have to, aren't we? Because that was in Algebra 1 too. We have to do all of Algebra 1 here. We're doing good?
No. Algebra 2.
Resny,
When we look at it, 6.
this is such a bad time to have this class.
Why?
Because you're going to reteach all of this, right?
No, I'm not. I'm going to send you home and you're going to do it for homework. It's going to be great
It's not going to happen.
because you are dedicated students.
But do you believe that?
You were wrong with that statement.
Well, I'm going to have to hope for it because other than that, we're pretty much done. 0 equals 6 VB squared minus 32 VB plus 10. Oh my goodness, we can't be done because that is the quadratic equation, and using the quadratic equation is something we must do now. Dun, dun, dun!
So when you plug that in with like
Which
the
one
calculator,
do
do
you
you use
use?
the
Yeah, you
small
have
number or the
You're going to get 2. Yes, what?
do you use the small one or the big one?
I'm not going to. Let's do it because physics has to make sense, right? So we're going to do it right now. So I'm going to go menu, equation, polynomial, second degree. Oops, that's not right. Let's try 6. Let's try negative 32. Let's try 10. Enter, enter. And I get 5, and I get 0.33333. Now, in the past, we've always said which one makes sense. Guys, you have to listen because this is also hideously important because it's the last bit of physics in it. Well, wait a second. This is for a VB, right? The big ball. So after the collision, the big ball is either going 5 or 0.333. Now, listen very carefully. These two equations only predict that momentum and energy is conserved. They don't predict anything else. They don't even talk about a collision happening. So one of your two answers is always going to be this ball missed this ball, and everybody's living happily ever after. So one of these two answers is always going to be your original number. If it's not, you've done something wrong. Because there's only two ways to conserve momentum. Elastic collision or they missed each other. It's always going to select they missed each other, or one of these two is going to be they missed each other, the other is always going to be they hit each other and they collided elastically. Yes, sir?
Couldn't you have just skipped all this and realized that the one on the left is bigger and going faster? So wouldn't it win?
Well, there's a lot of dicey things to go with that. Yes, sort of.
Well, isn't it usually?
What do you mean by win?
I mean, it's going to be the one that keeps its speed, the 5 meters per second.
Right. But this gives you direction. Well, yeah. Oh, sort of. Except, why would you assume it's 5? Because it's also big. 5's bigger, right?
It was going 5 original.
Okay.
So
Well,
we
then,
say-
as long as you put the originally part in there, I'm with you.
So it's the one
Okay.
that's not the original.
That's one that's not the original, the one we're interested in. This is nice, but it's not the right answer. We know it's the other one. So I'm going to take this, I'm going to plug it in here, and I got the speed of the two balls. Remember, I'm plugging it right back in here, right? Because we had an equation for the little ball.
So this is the big ball speed.
So our big ball speed is 0.333 after collision. The little ball is going to be 8 minus 2 times 0.333. And I get 7.334 meters per second for the little ball.
Wait, but how do you know which direction?
They're positive numbers.
No, but it says speed and direction. Like
They're positive numbers, so they're going to the whichever direction the first ball is going in.
straight.
We drew it to the right. Oh, that's interesting. Yeah, no, it's just to the right. Oh, it's the same direction the original ball was going in. The big fat ball was going in. Does it make sense? All right, try the next one.